Hello, today we'll be talking about Physics 51 Lab 4 about oscillations. As a preview, we'll be talking about, we'll have an intro, equations, I'll talk about um, the experiment versus computational model, results, and the discussions at the end. To start, the purpose of this lab is to predict the motion of our system with a spring and mass demonstrating our fundamental principles. The fundamental principles we have Newton's second law, the energy principle. Our system we have spring, mass, earth, and surrounding is nothing because there's no change in energy due to the energy principle. Uh, we understand that there's a spring force acting on the mass that's proportional to the spring of stretch. We also understand that the energy principle that the total energy of the system will be zero and will be made up of the change of kinetic, gravitational, and potential spring energy, which will oscillate and change within the system to maintain the net of zero energy for the results. Next, we saw the relevant equations, all based on Newton's second law and the energy principle. We see the energy equation, the update formula, and how we found the period of oscillation, and which we need for our calculations on the right. In the recording of an experiment with a spring and mass motion, we use tractors to record the system's motion. The initial conditions for the experiment are at the time of 0 seconds. Our initial velocity at 0 meters per second. Our position at um, negative 0.125 and negative 0.698 in 0 meters. We use 9.8 meters per second squared for gravity, a mass of 0.402 kilograms, and found the spring constant of 6.1 and the relaxed spring length of 0.126 meters using the equations from the previous slide. We set up the coordinate system, length, scale, and time between frames and recorded the center mass for the mass of each frame to get the data we will use to compare within our computational model. In our computational model, we considered our initial conditions and equations for kinetic, gravitational potential, spring potential, and total energy as seen on screen. This allowed us to find the initial energy to which we could compare it with to check and verify the energy principles were present in our computation. Entering into our while loop, we found the net force and used Newton's second law to update the objects for velocity and position, and we updated our spring as well as the force of the spring equation. We finally calculated the energy changes using the same equations as before and found the difference between the current energy and initial energy relative to our system. When putting our data, we can see our experimental x and y positions are very similar to that of our model based on the overlap of the position data seen in the respective graphs on the right. Additionally, when looking at the change in energy versus time, we see that delta E remains zero and the spring gravitational potential energy is oscillate and the kinetic energy also oscillates at twice the rate. This demonstrates the energy principle and that our total energy remains zero while components of the total energy alternate, which we would expect based on this fundamental principle. Some potential for errors, the differences between the selected versus actual numbers or actual center of mass and collecting data, and the potential for error resistance to impact the total energy within the system. I'm going to answer some discussion questions for our first one. What does this mean for our model, the system? The energy principle is satisfied. We see the total energy remains zero throughout the duration of the computation in the image, and the changes in kinetic and potential energies always balance out throughout by oscillating at appropriate rates. For the second discussion, what does this mean? For number two, we see that when we're looking at the x position of the period, we would get 1.619 seconds. While when looking at the y position for the period, we get 1.547 seconds. This would impact our calculations of the spring constant and the relaxed length because t is used to find k and k is used to find that relaxed length. This discrepancy can lead to unpredictable errors compared to our expectations, and you should be aware of this difference when considering the period to use when making our computation. And in conclusion, we have seen Newton's second law of the energy principle in action in this mass.